Okay, so we've been talking about all this graphing stuff, okay? And as we've been doing the graphing stuff, we've been looking at the different types of motion that are going to be involved in all the physics that we do going forward, okay? And those two types of motion are uniform motion, where something travels at a constant velocity, and non-uniform motion, where the velocity is not constant. In other words, the object's accelerating, okay? So what we're going to look at today is what acceleration is, because that's kind of an important part of the lab we did yesterday. I know that might seem backwards, but I really had a feeling we might not be here today, so I did the lab yesterday, okay? I was actually really afraid of that. So we're going to talk about acceleration today. What we learned today will probably help a little bit with the lab, okay? So, a couple of things we need to talk about with this. First thing is inertia. How many people have heard that word before? Okay. What is it? No clue. Just heard the word. Okay, that's all right. Okay, I didn't expect any of you to know what it was. All right. Inertia is the tendency of an object to continue doing whatever it was doing in the absence of any unbalanced forces. Okay? It's also known as Newton's first law. Okay? Now, Newton's first law is by no means a complex mathematical idea. Okay? Newton's first law says that this desk that's in front of me right now is going to stay right there. Shocking, right? Like totally rocket science. Okay? An object at rest will remain at rest unless it is acted upon by an unbalanced force. Okay, are there forces acting on the desk right now? Yes, but they're not just uniform, but they're balanced. Right, there are two forces acting on the desk right now. The obvious one is gravity. Gravity is pulling the desk down, but the desk doesn't fall because of the... Actually, weight is the force of gravity. Yeah, okay. That's a good guess. Okay. What keeps the desk from falling? Floor. Right? It's sitting on the floor. Gravity pulls it into the floor, and the floor pushes back with an equal but oppositely directed force. Therefore, the forces are balanced and the desk doesn't move unless I come up and kick it. Right? Then there'd be an unbalanced force, and the velocity of the desk would change. Okay? But right now, the desk has a certain amount of inertia. Okay? Could I move that desk easily with a small amount of force? Yeah, because the desk's not very big. It's not very heavy. It doesn't have a lot of mass. Okay? Inertia is really measured by mass. Okay? If I had a dump truck sitting right in front of me, it would also not do anything until there was an unbalanced force acting on it. If I pushed on the dump truck, I'm probably not going to move it. Or at least not like I could move the desk with the same amount of force, because the truck would have more inertia, and as a result, it would be harder to change its inertia, okay? To change its velocity and make it do something else. Does everyone kind of follow me there? Okay? Would you have to do more work to move the truck than the desk? Definitely, because you'd have to exert more force. The truck is simply bigger. All right, so that's inertia. Basically, you just need to understand that. There's no math to do with that. You're never going to get a problem to solve to do with inertia. Okay? As long as you understand that things just don't move for nothing, you understand inertia. Okay? Here's the second part of inertia. An object traveling at a constant velocity will continue to do so unless acted upon by an unbalanced force. This one's harder to get our head around. The reason it's harder to get our head around is because we don't see objects ever do that. If an object is moving and there's no forces acting on, and it doesn't seem like there's any forces acting on it, it eventually what? It eventually slows down and comes to a stop. Well, that's because there is, or are, unbalanced forces that are acting on it. The most common one would be friction. Yeah, we don't always see that, okay? But we can see that in low friction environments, things have a greater tendency to keep going than things in high friction environments, okay? Like if you ever watch paint drying, curling, okay? You've seen this, right? Like the rock it slides and slides and slides and slides and slides, okay? And it takes a long time for it to stop because ice is a low friction surface, okay? And in fact, and much of paint curling, okay, is actually channeling that force of friction to make the rock do what people want. Okay? In other words, if you've ever seen it, people sweep in front of the rock. Okay? The sweeping melts the ice in front of the rock and makes a very thin layer of water on top of the ice, which lowers the friction that the rock can experience. So now the rock will travel further. A very skilled curler can also steer the rock by sweeping. Okay? They only sweep on one corner of it, which reduces the friction on that side and actually makes it turn the other way, because there's more friction on the other side of it, causing it to rotate and slow down more in that direction. So a really skilled sweeper, okay? Is that what they're called? I don't know, I don't watch curling. Okay, anyway, this is how it was explained to me by Mr. Patrick, who loves paint jar curling. Okay, all right. So you can actually steer the rock because you can change those forces, those unbalanced forces. Okay? If you were in space, though, and you were already moving, would you ever stop? Not unless you came into contact or near something that could exert a gravitational force on you. No, you would float away. Okay? That's a real problem. Okay? Astronauts have to be mindful of that. Okay? If they're not tethered to their spacecraft, there's a real possibility that they could get moving and not be able to stop, because flailing your arms in space does absolutely nothing. Okay? It just makes you look panicked, which you probably are, okay? But it doesn't help. There's no air. Even in water, flailing doesn't really do very much. Okay? But in space, it does even less. And in space, no one can hear you scream because it's a vacuum. It's true. Okay? All right, so these are all things about inertia, okay? So if something's moving at a constant velocity, it'll continue to do that as well, unless there's an unbalanced force. Usually there is on Earth friction, okay? Uphill or downhill or whatever, okay? All right, so to acceleration. Yesterday we talked about the definition of acceleration because it was going to be part of your hypothesis in the lab, okay? Whenever the velocity of an object is changing, we say that the object is accelerating. Okay, so average or uniform acceleration, okay, means that the object's velocity is changing by the same amount every second, right? A really good example of that is a falling object or a plane, okay? A car is actually a really poor example of uniform acceleration, and we kind of saw this yesterday in our lab, because if you looked at all of your graphs, the dots did that. They kind of leveled off, okay? Your line ended up doing something like this, okay? So the cars weren't demonstrating uniform acceleration. They were accelerating, but it wasn't uniform. Why?
Well, this is just a guess. At a certain point, the car is struggling to go faster because of the amount of friction that the tires are generating with the ground. It's making it do more work to go forward.
You're on the right track. There is friction in play, but actually the friction is early on working for the car, and as the car moves faster, working more against it. Okay? As you reach your top speed, part of the reason you hit a top speed is because you can no longer exert enough force to overcome the force that's opposing you, and so as a result you cease to accelerate. Early on, you exert a lot of force, okay, and you accelerate very rapidly. But what else do you have to change in the car as you accelerate? Gears. Now, you guys, how many of you actually know how to drive a stick? Yeah, that number gets smaller every year. Okay, the stick shift is going the way of the dodo. Okay, but cars, even if you don't have a stick shift, still have a transmission. They still have gears. Okay, well, in first gear, okay, you can accelerate really hard. Okay, second gear less, third gear less, and so on up the transmission. Because I mean now there's like 10-speed transmissions, like a bike as opposed to a car. Okay, but you've got transmissions that have lots and lots of gears. But as you get to the higher ones, they don't have as much torque. Okay, they can't produce the same amount of acceleration, so you don't accelerate as much, which is why the slope of these points gets flatter. Okay? There's eventually going to come a point where the car reaches its maximum speed and this line would become flat. Okay? Obviously, this line takes an average of all the points and shows us the average acceleration of the vehicle over the entire graph. Okay? So that's not uniform. A plane, which doesn't have gears, as it accelerates down the runway, has pretty uniform acceleration, because the pilot just pushes the throttle all the way forward and accelerates down the runway at maximum power. Okay? And so that acceleration will be very uniform. Something dropped will accelerate very uniformly until it reaches terminal velocity. But in a vacuum, it would like fall straight, okay? And fall like at 9.81, doesn't matter what it is. Okay? Everybody kind of with me there? So, the formula we need to understand, and we've actually already used it a little bit in our graphing, is this one. A equals VF minus VI over T, which is sometimes written delta V over delta T. Okay? Delta is the Greek letter D. Okay? And it means change. So anytime you see the little triangle, it means final minus initial. Okay? So anytime you see the triangle, it means final minus initial. So that actually means that this formula is VF minus VI over TF minus TI. It's just the initial time is usually what? 0. So we don't ever write it that way. Okay? All right. So let's look at an easy example here. Okay? Let's say that for this plane, okay, we've got an initial velocity of 0. The question actually says starts from rest. That's a term you're going to need to know. Rest means stopped. Okay? So if something starts from rest, VI is 0. If it comes to rest, VF is 0. Okay? But the word rest means 0. Okay? It's not moving. Okay? Our velocity is 0 if you see the word rest. Okay? All right. So the plane accelerates down the runway and after 29 seconds attains a velocity of 260 kilometers per hour. Okay? And that's positive. So it's going forward. Right? We want to determine the acceleration of the plane using this formula. So here's what we do. Okay? A equals VF minus VI over T. We know VF is 260 kilometers per hour. Normally, we wouldn't do what we're about to do, but we're going to do it here because just to simplify things. Minus 0 divided by 29 seconds. Okay, how many times have I told you your units have to match? Right, like if you're doing a V equals D over T calculation, your D couldn't be in kilometers and your T in seconds, right, and stuff like that, or your velocity in meters per second, you couldn't do that, okay? That's somewhat true here. We would very rarely ever write an acceleration the way we're writing, but it's also not incorrect to write it the way we're going to write it. Okay, so if I go 260 minus 0, that's 260, okay, and then I divide that by 29, sorry, it'll take a while, my calculator takes a long time to fire up now. We're going to get our acceleration eventually. Okay, so 260 divided by 29. All right, so I get 8.97. What are my units? Kilometers per hour per second. Okay, now we were saying the other day that we always call it meters per second squared. We would do that provided we had meters per second as our velocity on the top. It's not technically wrong to say this thing is accelerating at 8.97 kilometers per hour per second. That's how many kilometers per hour it changes its velocity by every second. It's not incorrect. It sounds weird and it looks weird. Okay? So we don't normally do it, but it wouldn't be wrong. All right. Everybody okay with how that works? All right. Here's something we haven't done yet with this formula. Manipulate it. Actually, we have, because we've done y equals mx plus b a whole bunch of times, and this is really just right? If I'm looking at a velocity versus time graph, this formula comes from there. All right, but we'll look at how we manipulate this formula here for now. All right, so A equals VF minus VI over T. I want to solve for T. What do I do? Isolate it. Okay, where do I put it? Do I want to leave it on the right or do I want it on the left? I want it on the left because on the right it's on the bottom. Can't solve for something if it's on the bottom. Okay? So how do I move it over to the left? Multiply by, right. Okay, right now I'm dividing. If I want to move something, I do the opposite. So I multiply this side by t. There's a t on the top, there's a t on the bottom. They cancel. I multiply this side by t. All right, I want to get t by itself. I'm multiplying it by a. How do I move a? Divide it. Okay, t equals vf minus vi over a. Everybody okay with that? Okay, that's not a whole lot different than the v equals d over t manipulations we were doing before. Okay, where this becomes different is if we have to solve for one of the velocities. So let's say I want to solve for vf. What should I move first? T. Move what's not attached first. T is not attached to vf or vi because it's underneath them, right? Okay, so I'm going to multiply both sides by t. All right, I want vf by itself. Now what do I do with vi? Add it, because I'm subtracting it. If I want to move it, I do the opposite. Okay, so adding vi to both sides. Okay, I get this. Now, I want you to think about what this means. Right, I'm going to put the vi back over here. T times a equals the change in velocity. Everybody all right with that? Okay. So if I take the initial velocity, move it over here, and add it to the change in velocity, should I get my final velocity? Yes. Okay. Sometimes, I know for some people it helps if you can like talk an equation through, so that's kind of what I'm doing here. Okay. I'm trying to show you that this part of the equation equals the change in velocity. If I want to find out where I end, I take where I start and I add the amount that I change by. Okay, everybody all right with that? Okay, similar logic. If I want to calculate VI, I would take where I end and subtract the change. So could I just take T times A right over here? I could, yep. Okay, I can just subtract it over to that side. And that'll give me where I start. Okay, so those are the manipulations of that formula. Okay, so a little bit of algebra review there. All right, we talked about this the other day. I showed you this. How do we get the units meters per second squared? Okay, so if I have meters per second and I'm dividing by seconds, that's this part here. Okay, when I divide fractions, I reciprocate and multiply. So that's what's going on down here. Meters times 1 is meters. Seconds times seconds is seconds squared. So meters per second are usually written this way and usually spoken that way as well. It's usually said meters per second squared. Okay. Questions on the units? That's kind of review from the other day too. All right, we already did that. Okay, I want you guys to try this one. Okay, this one's easy because it's just like the plane question we did. Okay, so sprinter starts from rest. Remember what that means. Okay, and reaches a velocity of 16 meters per second in 4.5 seconds. I want his acceleration. All right, so like any other problem-solving question that we might get, okay, we want to write down our givens first. VI is 0 meters per second because they start from rest. Okay, they reach a velocity, that would be final velocity, of positive 16 meters per second, and that happens in a time of 4.5 seconds. I'm looking for acceleration. All right, so here's why you get a mark for your givens. Now we're using 2 formulas off of our formula sheet. By the end of this unit, we'll be using a dozen formulas. So writing down your givens helps you to decide what formula to use. All I have to do is go to my formula sheet and find a formula that's got these 4 things in it. Okay? When I find that, that's the one I want to use. All right? So A equals VF minus VI over T. I don't have to manipulate it. It's already set up to solve for A. So all I have to do is plug in my numbers. 16 minus 0 over 4.5. 3.6, what are my units? Meters per second squared. Okay. And do I need a direction on that? Is acceleration vector? Yes. What direction was I given here? Positive. Okay. On your final answer, make sure your vector matches what was given in the question, because sometimes we're going to turn up and down into plus and minus mathematically, right? Like if I'm doing this calculation, I don't write 16 up minus 0 down, okay? I don't put those directions in here. I have to represent directions mathematically, positive and negative. So when I finish my answer, if I get positive, that's great. But then I got to look up here and go, okay, positive was north, negative was south, and then I have to change back to what the question gave me. It doesn't come up very often, but just be mindful of it when it does. All right, any other questions on that one? Okay, then try that one. Now you're solving for time. All right, so as always, we want to write down our givens, okay? So we want to calculate how long it will take. What am I being asked to find? Time. Okay, to accelerate from rest to 85, positive 85 meters per second at a rate of 22, positive 22 meters per second squared. All right. Everyone okay with my givens? Because they never outright say the acceleration is 22 meters per second, but I have to understand that rate of change of velocity is acceleration. That's one of those spots where the definition of acceleration comes in handy. All right, so the formula I'm using here is A equals VF minus VI over T. And I want to isolate T. I cannot solve for it on the bottom, so I need to multiply both sides by T. That'll make it cancel over here, and I do to one side what I do to the other side. So I multiply both sides by T. All right, now I want to get A out of here because I want T isolated. So I divide both sides by A cancels and appears over here now, okay? Because I divide the other side by A as well, all right? So T will equal, okay, VF minus VI, so that'll be positive 85 minus 0 divided by the acceleration, which was positive 22. So 85 divided by 22. Okay, so 3.86 meters per second. Sorry, just seconds. 3.86. Yeah, 3.86 seconds. Okay, do I need a vector on seconds? No, time is scalar. All right, questions on how we did that one? Okay, we still haven't run into one where direction is important. Yes, we've had to put a positive on our answers here, but we haven't run into an acceleration question where the object changes direction yet. Okay, how will that change?
Will you have to do the device one for each direction?
Nope, actually I won't. Okay, if the object changes direction, VF and VI will be opposites, right? So if VF is north and VI is south, okay, then one of them has to be negative. I just decide whether I want north to be positive or south to be positive, and I assign it. And then I have to look at my acceleration as well. Okay, if it's accelerating north, then I have to make sure that my acceleration has the same vector as whatever I decided north was going to be. Usually north is positive and south is negative. Usually. Okay. All right. Okay, so this one doesn't involve that. Everything's still positive. Sorry, I thought the next question involved that. Let's do the next one. Okay, so this one here, we're just looking for the final velocity, and then I think I have one that asks you to find initial velocity, and I think it has a change in direction, but I don't remember. All right, so give this one a try. Looking for final velocity, you're given, okay, the other three. See how you do with that one. Okay, so we're looking for final velocity in this one, so that's our question mark, okay? A race car starts at positive 15 meters per second. So this is our first one where VI isn't rest. Okay, so we actually have a value for VI on this one. And it accelerates at positive 7.2 meters per second squared for 6.5 seconds. All right, so A equals VF minus VI over T, and I'm looking for VF. So what do I move first? T. T's not attached to VF, so I can move it first. All right, so I'm going to multiply both sides by T. All right, what do I have to do with VI? Add it over to the other side. Okay, so my initial velocity plus the change in velocity gives me the final velocity. All right, so VF equals positive 15 plus 6.5 seconds times 7.2 meters per second squared. All right, I don't usually put the units in my actual calculation. You don't have to either unless you really want to. Okay. All right, so we're going to have 15 plus 6.5 times 7.2. All right, so the final velocity is going to be positive 61.8 meters per second. All right, questions on that one? That's good there? Okay. All right, this one also doesn't have a change in direction. I think I did one where we had to do each manipulation of the formula before I started throwing monkey wrenches in the system. Okay, so this one here, you're looking for VI. Okay, so give that one a try and let's see what we get here. Okay, so for this one, we're looking for the initial velocity of the boat. Okay, so we're looking for VI. And it accelerated to positive 30 meters per second, so that's VF. Okay, at a rate of positive 2.6 meters per second squared for 8.9 seconds. All right, so A equals VF minus VI over T. Okay, and when I plug that, so I have to manipulate for VI, so I'm going to first move T over here. Okay, then I'm actually going to add VI over to this side. I know that seems counterintuitive right now, but there's a reason for it. Okay, I'm going to add VI over here. The reason I'm doing that is because I don't want to solve for VI as a negative number. Okay, I don't know about you, but for me, if I do that, I forget that it's negative and I screw up the direction. Okay, because that always happens. Right, so what I do is I bring it over here by adding it so that now VI is positive, and then I just subtract T times A over to the other side. Now I'm solving for a positive number instead of a negative number. If you can remember it's negative and solve for it the other way, that's fine. Okay, so I'm going to have, when I subtract T times A, it's going to come over here, and I'm going to end up with this. VI equals my final velocity minus the change in velocity. Okay, and that's going to look like this. So 30 meters per second, okay, minus 8.9 times 2.6. Okay. All right, so I added instead of subtracted. See, stupid. Made that same mistake. 30 minus 8.9 times 2.6. I don't know what's going on here, guys. Minus 8.9 times 2.6. All right, so my initial velocity is 6.9 or 6.86 meters per second, and it's positive, because I didn't end up with a negative number here. All right, everybody good with that one? Okay. Now, something I want to point out to you, I'm actually seeing it on a couple of your labs right now, and it's not really your fault, but I'm seeing it happen on a couple of labs. Okay, on your calculator, if you're using a formula like this one, okay, where you got VF minus VI over T, and you're solving for A, when you punch this into your calculator, the top has to be in brackets. If you don't, what will your calculator do? it'll divide first. Your calculator is programmed to perform order of operations, and it'll divide before it adds and subtracts, and that is not going to get you the same number. Okay? And it happened to a few of you on question number 3 on the analysis of the graphing lab. Okay? You had, you were solving for x, and you had y minus b over m, and I think you just typed it straight into your calculator that way, which gives you a different answer than this does. Okay, is everyone following me there? So I don't think I ever pointed that out, so I'm just pointing it out now. Okay, order of operations is what your calculator defaults to. Okay, I've only seen it a couple of times. It hasn't been a big deal, okay, but I don't want it to become a big deal, so I'm pointing it out right now. Okay. All right, this one. Don't look at the answer. Okay, this one involves a change in direction. Okay, we have to keep that in mind when we're doing this. So, a ball is rolled up a hill at 4.5 meters per second. So what's VI? Four and a half up the hill. Okay, so VI is going to be 4.5 meters per second uphill. Okay, I'm going to assign positive to uphill. Okay, because I can't put uphill mathematically into a formula. All right, because the only other direction I'm given is downhill. There's no sideways in this question. All right, so I just have uphill and downhill. Those are exact opposites of each other, so one can be positive and one can be negative mathematically. All right, so I'm just going to say uphill is positive. All right, and then it accelerates down the hill. So my acceleration is 2.1 meters per second squared downhill, which means mathematically it's going to be negative. Now, I don't usually do this, okay, like put the positive and negative beside it. I'll usually just write, you know, negative here, and then I'll just underline, okay, in the question for myself, but okay, just illustrate here. What is its velocity after 3.5 seconds? Okay, give that one a try. That's the answer, I think. So you'll know if you did it right. Okay, so give it a try. Right, you are looking for VF. are we ready to go over that one? Yeah. All right, so we're looking for VF. We got A equals VF minus VI over T, okay? So we manipulate for VF, we multiply both sides by T, we add VI to both sides, right? We've got VF. Here's where we have to be mindful of direction, right? So when I'm solving for VF, I now have to keep in mind that 4.5 meters per second, VI, is positive. So I've got positive 4.5 plus 3.5 seconds times 2.1 meters per second squared downhill. So times negative 2.1, right? What this is going to do is, okay, for every 3.5 seconds, it's going to decrease my velocity by 2.1 meters per second squared, or by 2.1, sorry, meters per second, and then add that to my initial velocity. Okay, so it's going to take this, calculate the change in velocity, which is going to be backwards, okay, and add it to this, which is why I'm going to end up going backwards at 2.85 meters per second. So when I punch this into my calculator, 4.5 plus 3.5 times negative 2.1. Negative 2.85. Now, when I write that as my answer, I don't write negative 2.85, I write 2.85 meters per second downhill. Okay, I match the vector given in the question. Don't think I recorded. Oh, I did. Good. I remember to start it. All right. Questions on that one? That's about as tricky as they get. If you're looking for some good news, that's as tricky as they get. Okay? The only challenge there is to acceleration problems is knowing what you're given, manipulating the formula. Occasionally you got to do this vector thing. Okay? That's really it. Don't use triangles. Triangles won't work here. Okay? You have an addition subtraction operation. The triangle won't work. So if you're still trying to figure out how to use the triangle, stop figuring out how to use the triangle, figure out how to do algebra. I'll help you. Okay? You got to remember the algebra rules. Okay, let's have you guys try this one. Okay, object thrown up in the air at an unknown velocity. It is in the air for 6.5 seconds, and its final velocity is 2.4 meters per second down. Okay, acceleration due to gravity is 9.81 meters per second squared down. Okay, what is the initial velocity? So we got plane lands on a runway, okay, at a velocity of 200 meters per second. Okay, so that's our initial velocity. Over a 15-second interval, okay, it slows at 6.5 meters per second. What do I need to write about that 6.5 meters per second squared? It's negative, okay? That's a trick that we got to be on the lookout for, okay? We're looking for the final velocity of the plane. Well, VF will be, okay, VI plus T times A, okay? And when we plug that in, it's 200 plus 15 times negative 6.5, okay? And that'll get us our answer for that one. All right, if I can get everybody to clear off their desk and mask up, okay, I'm going to come around and spray your desks.